chemistry fans. So today what we're going to have to do is demonstrate a little knowledge about buffers. So this is Unit 13, Topic 6 homework. Let's jump right into it. Let me share my screen with you and we will get started. So here is the problem, and let me get my calculator out. So in this first one, we're doing a neutralization problem. And so you're given the values for both an acid and a base. But what we got to pay attention to is this little detail right there. How many of the acid particles are there? How many base particles are there? So our formula basically is molarity of acid, volume of acid equals molarity of base, volume of base. However, when we are dealing with multiple hydrogens, there are two, we have to take that into account with the number of moles of H because it's releasing twice as many H's as it is over here with the bases. So they are flipped. The bases go with the acids go with the bases on the number of moles because it's a 2-to-1 ratio. All right, so now we're just going to go ahead and plug in. There's one of the OHs. The molarity of the base is given to us 6.96 times 10 to the negative 4, and there are 35 milliliters of it on the, sorry, that was the base value. I put that in the wrong place. So that is going to be on the acids. We'll have two acids. So now let's come over here with the bases. I will have one OH, and my molarity is 3.51 times 10 to the negative 2. We don't know the volume of the acid. So we're plugging all this into our calculator to solve. So I've got 2 times 6.96 to the negative 4 times 35 divided by 3.51 to the negative 2. And what you get is a volume for the acid, which is equal to 1.4 milliliters. Not a whole lot of milliliters at all. That's just a very small amount to neutralize that. All right, so that's number one. Number two, we've got a buffer problem. So there is something that we learned about called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation goes something like this. So we've got the pH is equal to the pKa plus the log of the base over the acid. Now, this goes back to where our definition of the acid and the base is. So here are two materials, and hopefully at this point, what you can start to recognize, they both start with H. You're absolutely right. But in the way that this is written, the sodium and the hydrogen at the end are the differences. These are going to dissociate into these formate ions, polyatomic ions, HCOO, but notice there is a missing H, which is being fulfilled by the sodium then over here. This is creating the buffer situation. So our acid is the material that has the extra H. So the value for that is a 1. What we don't know is the value of the concentration of this buffering material. How much of it are we going to have to put in here to get this pH of 3.5? Our pKa is where we have the same idea of a pH. It's the negative log, not of the hydrogen ion concentration, but of the dissociation acid constant. So we're going to plug into this the negative log of 1.77 times 10 to the negative 4. 1.77 times 10 to the negative 4. And what you're going to get there, let me plug that in, negative log of 1.77 to the negative 4. And you get 3.75 is our pKa. And then we're going to take the log of this x over 1. Okay, so we have all of our values. We've just now got to try and clean this up through some algebra here. So what we're going to do is we're going to subtract 3.75 from both sides. And that's going to cancel that out over there. And what we'll end up with is a negative 0.25 is equal to the log of x over 1. So what we got to do next, got to get rid of that log. So what we're going to do is we're going to do the inverse log. So in other words, 10 to the power of this negative 0.25. And anytime we take the inverse log times the log, well, those things cancel out. So what we'll end up with here is on your calculator, this is going to end up being 0.562 is equal to x over 1. Well, now it's just a simple task of cross multiplying. So our x is going to be equal to 0.562. So now this, what is this? This is the molarity of that original material. If we go up to the problem statement, this is the molarity of this right here. But we're not asked for that. We're asked for how much. So what we got to do now is go to our molarity formula, which is moles over liters. They tell us in this problem that we are given 400 milliliters. That becomes 0.4 liters. So I've got 0.562 equals x over 0.4. So we multiply those together. So point times 0.4. Whoops. Go to second answer times 0.4. We get the number of moles is equal to 0.224. Okay. Well, now think about the mole map. And to go back out to grams, what we're going to do is we're going to multiply. What do we multiply by? The molar mass, and they tell us the molar mass is 68.0069. So multiply that by 68.0069, or just multiply it by 68. And so that becomes 15 grams is what our answer should be after that point. So here is our final answer. You are going to need 15 grams of this sodium formate, sodium formate. We're going to need 15 grams in 400 milliliters, along with the 1 molar solution of the formic acid, and that will create this buffering solution that maintains a pH of 3.5. All right, so lots of calculations going on, very complicated. Thanks for staying with me. Thank you very much. One problem. Talk to you again soon. Bye.